Hi everyone, we start with chapter 2, Boolean Logic, and we're going to cover the topics Boolean operators, truth tables, logic gates and circuits, laws of Boolean algebra, and De Morgan's laws. Now, George Boole, the mathematician, came up with the Boolean logic, which is a form of an algebra in which all values are reduced either to true or false. And this is important for computer science, where it fits in very nicely with the binary numbering system, in which each bit has a value of either 1 or 0, which we could consider 1 as true and 0 as false. So let's look at the operators. The AND operator is basically an operator where if the inputs are both the inputs are true, the output is true. Otherwise, the output is false. So in case both inputs are false, obviously it's false. Even if one of the inputs is true, it will still remain false. It's only when both inputs are true, the output is true. And if we convert it into a truth table with zeros and 1, then if both the inputs are 1, then the output is 1. In case both are 0 or one of them is 0, then the output is going to be 0. And the symbol that we write is the dot most of the times, but other symbols that are used are ampersand and the caret symbol. So if we say x, y as inputs, then the output for AND will be x dot y. We come to the OR operator, or this is also called the inclusive OR operator, and it is written with the plus sign, or in some cases it's written with the V or double pipes. Now, in this case, if both the inputs are false, the output is false. In case one of the inputs is true, the output will become true. And of course, if both are true, then the output is also true. Only when both are false, it's false. So if we take zeros, then both the inputs have to be 0 for the output to be. We come to the NOT operator, which works like a reverse switch, where if you take a value 0, it is turned into 1, 1 is converted into 0, basically the complement. And we use the exclamation mark or the negation or the tilde symbol to show NOT. Exclusive OR is basically when both the choices are not the same. That means if both are false or both are true, in that case the output will be false. It's only when both are opposite to each other, then this becomes true. So it is an OR, but an exclusive OR, hence we write XOR operator. And the symbol that we use is the plus sign, but with a circle around it. The NOR operator is that neither of the choices is true. That means this is going to be true only when both the inputs are false. So if we have one of them true or both of them true, the output is NOT AND works in the way opposite to AND. Hence, it will be true only when both the inputs are false. And it is written with the same symbol x dot y, but with a bar on top, or you could also have an accent, which we will see later. Now we come to logic gates and circuits. Basically, it's a digital circuit with one or more input. We will see those in the examples. And the condition is basically only two conditions. Either the value can be 0 or it can be 1. And when we look at it in a simplistic way in the circuits, then a 0 volt is basically your 0 or low state, and plus 5 volts could actually symbolize your 1 or true or high state. So look at the AND gate, which behaves the same way as our logical AND operator. It looks like a huge D with two inputs and an output. But of course, in circuits, you can have more than two inputs. If both the inputs are 1, then the output is going to be 1. Otherwise, it's going to be 0. The OR gate behaves again the same way as the inclusive OR that we did when the inputs, both the inputs are false. That means that even if one is true, the output is true. We look at the NOT gate, which is basically a reverse switch. So if the input is 0, the output is 1. The input is 1, the output becomes 0. Now we'll look at some laws of Boolean algebra, and we'll also see some circuits with it. The annulment laws to start with. The first one is that if a variable is AND with 0, it's always going to give you a 0. So if you look at the circuit here, it says X and then 0 as input, and the output is always 0. And we can see this in a truth table. The AND operator with 0 is always going to give you a 0. The OR operator with 1 is always going to give you 1. So if we have the OR operator as X and 1, the output will always be 1. The identity law is basically saying that if X dot 1 is taken, then that means the AND circuit with X as one of the inputs and 1 as one of the inputs, then the output is always going to be X. And you look at the truth table, you'll be able to see that the value of X and X dot 1 is the same. Similarly, X or 0 will also give you X. And if we look at the truth table, we see the X is 1 or 0, and X plus 0 is also 1 and 0. So the output is X. The idempotent law says that if you say X and X, that means you AND it with itself, then the output is again going to be X. And this is also true in case of OR. So if you look at the truth tables, you will understand how X and X dot X have the same values. Similarly, X and X or X, that means X plus X, have the same value. And look at the circuit here. We have the input as X, and then we have X is branching out to give another input to the gate. Now we look at the complement law, where we say X dot and X complement, basically the opposite of what it was. So we're using X as 1, then the complement of X is 0. This is basically applying the NOT. And if X is 0, then X complement is 1. And this will always end up as 0. And in case of OR, if we take the complement, it will always end up as 1. So if you see the circuit, the input is X and the other input is with a NOT switch. That means to show that it will be the opposite of X. The commutative law says that X dot Y is equal to Y dot X. That means the order in which these variables, two variables, are using the AND operator, it doesn't matter. So the output in both cases, as you can see in the truth table, remains the same. That means X dot Y is equal to Y dot X. And similarly, X plus Y is equal to Y plus X. So in case of OR, this is also true. So the commutative law holds for both AND OR. The double negation law says that if you use two negative NOT switches, or you take the double complement of X, the value that you will get will be the same as X. The distributive law is actually the same as you see in math, where you say X dot Y plus Z is equal to X dot Y plus X dot Z. And if you look at the truth tables, you will see the output in both the truth tables is exactly the same. in the last columns, that is x dot y plus z is the same as x dot y plus x dot z. We now look at the and distributive law, where we have x plus y dot z in the bracket, which will be equal to x plus y in bracket dot x plus z. And we see that both the truth tables give us exactly the same output, which basically proves the distributive law. We come to the associative law, which, like in math, we have x plus y plus z in bracket or x plus y plus z in bracket. Any of these, you can change the order, put one in the bracket or the other in the bracket. It doesn't matter, because the output will remain exactly the same. And this can be proved using the truth tables. And as you can see, the logic circuits for the two are also given. And these truth tables get exactly the same output, which goes to prove that these two things are the same. We can use the and associative law exactly the same way. And here again, we have the circuits, and then we use the truth tables to prove this associative law, where we say x dot y dot z in bracket or x dot y in bracket and then dot z outside bracket. It doesn't matter, whichever way you write it, it will give you the same output. We come to another law, which is absorptive law, but this is basically kind of an example-like thing where we prove something using the earlier laws that we have already proved. So we have A plus A dot B is equal to A, which we have to prove, and this is the OR absorptive law. So what we do here is, in the proof, we write A dot 1, which is the same thing as A, and we say A dot 1 plus A dot B is equal to A dot 1 plus B. And here we are using the distributive law, and then we check that 1 plus B is also in our earlier laws. It gave us the output as 1. So A dot 1 gave the output as A. So we've used distributive, we've used annulment, and we've used identity laws to prove both these absorption laws, that is and or. We now come to the De Morgan's laws, where there are two statements and which have to be proven true. That is x plus y, the complement of this is equal to x complement dot y complement, and the law 2 states that x dot y, and if we take the complement of this, it is equal to x complement plus y complement. And if we prove the first law, we look at the circuit where we take first of all x and y in an OR circuit, and then we put a NOT switch in front of that just to find the complement of x plus y, and then we have to prove that this is equal to taking x through a NOT switch and taking y through a NOT switch, and then both these inputs to an AND operator will end up as x complement dot y complement. If we look at the truth table, we have proven that x plus y, the complement of that is not OR, is equal to taking x complement and y complement. That means x complement dot y complement, and the highlighted two columns that you see are exactly the same. So this is how we prove this. It's not difficult. It is just that when you actually do it, you will understand this even better. The same thing can be done with the second law, that is, we take x dot y, that is x and y, through an AND circuit, then we put a NOT switch in front of that is to make x dot y complement, and we have to prove this equal to x through a NOT switch, y through a NOT switch, and then we take them through the OR gate, and that becomes x complement plus y complement. And if we put this entire thing inside a truth table, we'll be able to prove that these two are exactly the same. And here we've done it through two highlighted columns which look exactly the same. So that brings us to the end of this chapter. I hope you understood. And I hope that you will continue watching the rest of the chapters. Do subscribe to the channel. I will see you soon.